So we have 1, and you're the only one. You can see if anybody else comes in. Looks like everybody's attending in YouTube right now, though. Okay. So first I need to apologize. Friday I gave out a quiz and I ended up giving out the wrong version of that quiz. So the version that I gave out had the answers at the bottom, and obviously it's not going to be able to count as a full quiz then. So again, I apologize for that. I don't know what was going through my head on Friday, but I messed up pretty bad there. I don't want to just disregard all that work that y'all did, because I know there was a fair amount of people who didn't realize that there was answers at the bottom of the quiz. So again, I don't want to throw out that work. So I'm going to use the grades from the quiz as extra credit grades. And then Friday of this week, we'll be having another quiz that goes over basically the same stuff, because I want to know how y'all are doing on this content so far. But it's going to be mostly the same stuff with a little bit added. Okay. So, what we've been going over so far lately is measurements of location. So, where we can see our data located. A lot of this is trying to figure out what is the best representation of our data, what is it doing overall, where can we find most of our data, things like that. So we've talked about mean, median, and mode, but those are just single values. And so these single values, if we say like our mean maybe is 5, okay, so most of the data should be somewhere around 5. Well, where around 5 is it going to be? Okay, how much space around 5 is most of our data going to fall into? So to help us figure this out, we have standard deviation. So the way you can think about standard deviation is if we have our normal distribution, so one of these bell curve things. Oh, there's somebody else. Okay. Our mean, median, and mode are all going to fall right there in the middle. So again, if we said that our mean is 5 for this example, most of our data, after all, we can see in this curve that as we get close to 5, it increases and increases and increases, then past 5 it starts to decrease. So somewhere around here is where most of our data is. Once we get a standard deviation, we can actually use that to find the area around 5, or around our mean, that our data is located. So from this mean to this boundary on this side is 1 standard deviation. From the mean to this boundary is 1 standard deviation. So there are 2 standard deviations, and standard deviations are a distance. So there's 2 of those distances, one on each side of our mean. And again, making that range like that, this is where most of our data is going to be located. So instead of trying to describe our data, typically it's going to be 5. Well, no, really it's going to be somewhere around 5. And standard deviation allows us to define where around our mean most of our data is located. Does this make sense? Okay, good. All right, so before we actually get into the calculation for standard deviation, I'd like to go over some symbols. So first of all, n. We've seen n before. We've been using n quite a lot. N is the number of data points in a set of data. So if we're calculating mean, we take all data points, add them up, and then divide by the number of data points we have. Well, the thing we're dividing by is n. So n is the number of data points in a set. Next, we have uppercase sigma. This is another one that we've mentioned. Sigma is telling us to do something. It's kind of like add, subtract, multiply, and divide. Those things are called operators. Sigma, what it's telling us to do is to take all the numbers in a particular set and add them up. So get a sum. And so when we're dealing with data in statistics in general, we're going to have lots of different types of sets of numbers. And when you see sigma next to one of those sets, it just means add all those numbers up. That's it. Next, we have x. When we look at tables of data, if it's just a single variable data set, so just, maybe 5, 9, 2, 12, 13, just a single variable, we call that set of data x. So each of those points in there is an x data point. So x, you can think of it as being any data point. Okay? Any questions so far? Nope, making sense? Okay. So at this point we need to start making some distinctions. Remember that there are basically two types of ways that we can collect data, either as a sample or as a population. So a population is where we have everybody in a particular group represented. So every single possible data point in a group is represented. So like the height of all NBA players, the number of pets owned by all people in Alpine. Okay? So these are populations. Samples are where, maybe we can't get all of the data points. Instead, what we can do is we can select some to take data points from, and then do statistics on that sample to project what might be true for the rest of the data. So project into the population. So, if we wanted to know the average height of human beings on Earth, well, we can't really take every single person. It's not really possible. But we can take a sampling of people from all over the world and then run statistics and get an idea for what the rest of the population might look like. Okay? So we handle population and sample differently. Okay, and there's some things that we do to keep it straight. Which one are we talking about? Are we talking about population or are we talking about sample? First, if we want to talk about a mean, a population mean, we call that mu. The Greek letter mu. If we're talking about a sample, yes sir. Some paper? Yeah, I can get you some. Yeah. Let me know if you need more. So for a sample, of course we can also calculate a mean for a sample, but again, to make sure we understand what we're talking about, whether it be a population or a sample, we call the mean for a sample, mample? How about mean? We call it X bar. So if we're talking about a population, we call the mean mu. And if we're talking about a sample, we call the mean X bar. And again, this is to help us keep, order on, are we talking about a population or are we talking about a sample? Standard deviation is similar. Standard deviation for a population is called lowercase sigma, or you can just call it sigma. But it's this circle with like a tail on top of it. And then standard deviation for a sample is just S. Okay? So they're talking about the same thing, mean and standard deviation. They're talking about the same thing, but we have different symbols for them. Particularly with standard deviation, it's quite important. Mean is calculated the same way. So for mu, we take the sum of all data points in the set and divide it by the number of data points we have. So again, we add up all the data points, divide by the number of data points we have. That's what this means. Sigma x is adding all those data points. Divide by n is just divide by the number we have. And it's the same for x bar. It's calculated exactly the same way. Standard deviation, on the other hand, is calculated differently. For a population, standard deviation is the square root of the sum of x minus mu squared all over n. Essentially what we're doing here is we're calculating variance and then taking the mean of that variance. Honestly, to me, I think standard deviation is more important, so I'm just kind of skipping over variance. Excuse me? Of a population?
Yeah, the standard deviation of population.
This. I'm not quite understanding your question.
The standard deviation of the population, right?
Yeah.
What is the symbol for that?
Oh, sigma. Sorry.
Oh.
Yeah. This is lowercase sigma. It's like a circle with a tail on top of it. Okay. So standard deviation for a sample, on the other hand, pretty similar with a key difference. We still have the sum of x minus the mean, x bar, squared, But when we divide it by n minus 1. Okay, so remember that in a population, we have all the data points for an entire group. Okay, we have everybody in that group, whatever we're measuring. Okay, with a sample, we don't have the entire group. We just have a part of the group. So that's why we have to use n minus 1, because we don't have the entire n. We have something approximating it. Okay? Any questions? None? All right. So let's try making a sample standard deviation. Okay, so again, we're going to take a sample and we're going to try to find what that sample can tell us about the population if we try to project that to the entire population. So remember that a sample, the mean for that is x bar, and we're going to need that when we work with our standard deviation. And it's sigma x over n. So add up all the numbers in our data set and then divide by the number of data points we have. Again, sigma, the uppercase sigma just means add all the points in whatever set this is. Then for our sample standard deviation, it's the square root of sigma x minus x bar, the mean, squared over n minus 1. So let's get some data to put into this. I've got one here I pulled from online. It says a sample of 4 students was taken to see how many pencils they were carrying. Odd thing to measure, but okay. So again, this is just a sample. It's not like an entire class, it's not an entire school, it's just 4 students. We're taking a sample. And when we saw how many pencils they had 2, another one had 2, one of them had 5, and one of them had 7 pencils. So when we're looking at mean and standard deviation, we want to find the mean first. And we want to do that because mean is used in the standard deviation formula. So we really need to find that mean first. So again, if we want to find the mean, x bar, we need to find the sum of all of our points. So add all of our points up. So 2 plus 2 plus 5 plus 7 is going to give us what? 16, good. What is our n? 4. We have 4 data points, good. So to get our mean, in other words, sigma x over n, it's 16 divided by 4, so what is that? 4, yeah. There's our mean. X bar, excuse me? Yes. We're talking about a sample here since we sampled 4 students out of the population. And that's why we were calling it x bar, because x bar is the sample mean. If we were talking about population, then it would be mu. It would be that curly U thing. Okay, so we got our mean, good. Now we need to use this mean to find our standard deviation. And of course, anytime that we're working with math, we need to use our order of operations. So first thing in order of operations, parentheses. So we've got x minus x bar. Now remember, x can be any data point. So what we're going to do to find x minus x bar is we are going to take each of these data points, each of our x values, and subtract our mean, our x bar value. So 2 minus 4 is what? Negative 2. 2 minus 4 again is negative 2. 5 minus 4? Just 1. 7 minus 4? 3. Okay? So we've done our parentheses. Next comes exponents. So we've got a square here, which means that we need to square all of these values. So x minus x bar squared. Let's see, square all these for me. So negative 2 squared. Negative 2 times negative 2. 4, and it's positive 4, right? Yeah, because negative times negative is a positive. Good. 1 squared.
So when we square like this. We square like, remember this.
So when we square it, we're saying, okay, we've got our x minus x bar. We got our x minus the mean. So we have a new set of numbers. When we square this thing in parentheses, what we're doing is we're squaring each of these numbers here. Yeah, so negative 2 times negative 2, 4. Negative 2 times negative 2, 4. Negative 1 times 1, 1. 3 times 3, 9. Remember that squaring means that we're multiplying the number by itself. So again, negative 2 times negative 2 is 4. Negative 2 times negative 2 is 4. 1 times 1 is 1. 3 times 3 is 9. Does that make sense? Good. Okay, so we've got our squared values. Okay, what comes next in order of operations? Well, we've got our exponent done. Before we move on to anything else, we really need to know this entire top part. Until we know the entire top part, we can't divide by anything. So sigma of all of that, remember sigma means what are we going to do to everything? Add everything up. Good. So if we do sigma of x minus x bar squared, that means we're taking all these numbers up here and adding them. So 4 plus 4 plus 1 plus 9 gets us what? 18. Good. Okay. So now we've got that top part done. Now we can divide it by n minus 1. Again, what is our n? 4. So what would be n minus 1? Yeah, it's not a trick question, it's just 3. So now we need to figure out this part. So 18 is what we have here on the top. We need to divide it by n minus 1, which we said was 3. So 18 divided by 3 is what? 6. Good. So we've got the top part done. We divided it by the bottom part. What's left? Top part's done. We divided it by the bottom part. What's left after we do all this fraction thing? Got to square root it. And that's the last thing we have to do. So once we do this, we'll have our standard deviation. Okay, so we need to figure out the square root of 6, and it's calculator time for that. So square root of 6, we get 2.449489743, whatever. It's a big long number. It's irrational. It has a decimal that doesn't repeat, but keeps on going on and on forever. So since we're talking about pencils here, I want to round this to the nearest whole number. So what is the nearest whole number here? Whole number? So 2, we look to the number next to it. Does 4 round it up? Yeah, it's just 2. So we can say that this is about 2.45, but when usefully, we're going to say that our standard deviation equals 2. So again, here's how we use that. If we use this on a normal distribution, so this nice even curve, our mean is right in the middle. And we saw that our mean was 4. So the average number of pencils a student have is somewhere around 4. Again, the standard deviation allows us to know how close or how far away to 4 those data points are actually going to fall. So for the typical student, we're going to be 1 standard deviation away from the mean in both directions. Imagine those are even distances. Okay, so this one is 2 further behind 4. So what is 2 from 4? 2. And this one is 2 further in front of 4. So what is 2 ahead of 4? 6. So we can say that, yeah, average, they're going to have somewhere around 4 pencils. But the standard deviation allows us to say they're going to have between 2 and 6. That's where most of our data is going to fall, is between 2 and 6 pencils. Okay, so if we were to select a student at random from our population, or even from our sample, they're going to have between 2 and 6 pencils usually. Sometimes they will fall outside of this because maybe you have a student who has just 1 pencil. But that's what we call an outlier. It lies outside of this typical range. So they might, have 1 or no pencils. They might have 7 to 10 pencils. Okay, but the typical person isn't going to have that few or that many. They're going to have somewhere between 2 and 6. And again, this is based on a sample. This is where taking a few people and projecting it for the rest of the people. Does this make sense? Any questions? None? All good? Okay. Then let's try a population. Okay. So again, I've got an example I pulled from online. So this one is a population. Here we have dogs in a kennel, and we want to know their heights so that we can use that data to understand what kind of kennels we need to build. How high do we need to build these kennels? How wide? Okay. So we've taken the population of the dogs at this pound or kennel or whatever it is, and we've gotten their heights. So in millimeters, we have a dog that is 600 millimeters tall from the base of their foot to the top of their shoulder. Another one that is 470 millimeters. One of them is 170. Another one is 430, and another one is 300. Okay. So again, we're calculating this as a population, all of the dogs in this facility. All right? So if we want to calculate this as a population, again, the mean is going to be mu, which just like x bar is the sum of all the points of data that we have divided by the number of data points we have. And the standard deviation will be sigma is equal to the square root of the sum of x minus mu squared over n. Just n, not n minus 1. Because again, this is a population. Okay. It's the exact same steps as a sample though. We first need to find the mean. So, we need to find the sum of all of our numbers. And since these are really, really big, I'll just do them for us. Okay? So the sum of all of our numbers is 1,970. And then our n is what? 5. We've got 5 data points. So our sum divided by our n, again, I'll do this for us since these are large numbers. 1970, divided by 5 is 394. So there's our mean, there's our mu. Okay, so we've got our population mean. Now we want to find our standard deviation. So like I said before, it's the same steps as we were doing with a sample. We need to take each of these data points now, x minus the mean. So 600 minus 394, 470 minus 394, 170 minus 394, so on and so forth. And again, big numbers, I'll do this for us. So x minus mu, let's see, we get 206, 76, negative 224, 36, and 94, negative 94. So we've gotten our data point minus the mean. So now we need to do what?
We did 600 minus 394.
Yeah. 600 minus 394 is 206. 470 minus 394 is 76. 170 minus 394 is negative 224, so on and so forth. So what do we need to do next with all these numbers? Not quite there. We need to figure everything on top first. So we've done in the parentheses. What comes after parentheses? Exponent. So we need to square everything. Good. So x minus mu squared. Again, big numbers this time. 42,436. 5,776. 50,176. 1,296, and then 8,836. So there's all of our numbers squared. Okay, so we've done in the parentheses, we squared them. Now what do we need to do with all these numbers? Missing one. Before we can divide, we need to do everything up here. So we've done the parentheses. Do the sigma, yeah. So add all these together. Good. So sigma of x minus mu squared. So add all these up, we get 108,520. Now what can we do? Divide. Yeah, there we go. Okay, and this one again, this is a population, not a sample, so it's just straight up n. So 108,520 divided by 5 for our n is going to give us 21,704. There's one last step that we need to take here. So we've gotten the top part done, we've divided by n, what's left? Square root. So take the square root of this thing. So square root of 21,704 is 147.32. Again, since we're talking about millimeters here, we don't need to go much smaller than millimeters, so we'll just do, standard deviation equals 147. What comes after millimeters? Micrometers? Something like that? Yeah. Don't really need to know that with the dogs. So, again, if we were to put this onto a normal distribution, okay, so right here in the middle of our distribution, if we have our mean, which we said was 394, and then we need to have one standard deviation on each side. So one standard deviation over here. We take 394 and do what with it? To find this part right here. This is one standard deviation away. So if our standard deviation is 147, we're going back behind this. What are we going to do? What are we going to do with 147? Subtract it from 349. Good. So subtract that. Let's see what we get. 247. And then the opposite for this side, we need to go one standard deviation up. So 349 plus 147, and I get 541. So most of the dogs in this facility fall between 247 millimeters tall and 541 millimeters tall. So as long as our kennels can facilitate those dogs, most of them are good. Now we do have some dogs that are up above that. They're outliers. And so a kennel that works for the dogs in this range might not work for these. So most of our kennels can be like this, but we might need like one or two that are, larger to facilitate all these dogs in the facility. So does this make sense? Any questions? Okay. Good. So, like I said before, quiz on Friday. It's going to be mostly the same stuff you saw last week, but we're definitely going to add in standard deviation. And I also want you to know your symbols. So I will have one or two questions on there asking you what a particular symbol means. Okay? I can just give you this. I don't have the COVID, so. All right, so I think that'll do it for today. Just prepare for that quiz. I'll see you on Wednesday. I hope you have a good one.